All right, so in this video, we're going to take what we learned previously about gradients and apply them now to a couple different areas. So one of them being the equation of a tangent plane. So remember, for the equation of a plane, we always need two things. We need a point and we need a normal vector. In the last video, we found out that gradients are going to be normal to all of the level curves of a surface. So therefore, in the context of what we're going to want, the normal vector can be used as the gradient vector. So when we come up with the equation of a tangent plane, instead of having traditionally the n being defined as a, b, and c, now we're going to be able to write it as f sub x times x minus a plus f sub y times y minus b plus f sub z, z minus c, equals 0, where those coefficients now are going to be the components from the gradient vector. All right, so we'll take a look at this example that's up on the screen now. We're going to find the equation of the tangent plane to the surface at this point. So really the only thing that we're going to need to worry about to start is that gradient of f. So the components here would be f sub x, f sub y, f sub z. So to get started, the f sub x would be a yz plus 2x. The f sub y would be an xz minus 4y, and the partial of f with respect to z would be an xy plus 3z squared. If we take this now and we evaluate this at 5, negative 2, 3, it's going to give us the vector with components 4, 23, 17. So this would be your f sub x right there, your f sub y evaluated there, and the 17 would be the f sub z. And then plugging it in would be the same as it was earlier in the course. We would have a 4 times x minus 5 plus 23 times y plus 2. And then we've got finally a plus 17, z minus 3 equals 0. And this would be an appropriate form for an answer you gave me, even though in my math I might want you to simplify that down a little bit. Now, I've taken this a little bit further than the book does early in this chapter by showing you the equation of the tangent plane. They actually reference the equation of a tangent line using the gradient. That information can be found on page 836 in the text, so I would encourage you to take a look at that. If you can understand this, then you'll certainly be able to understand the one on page 836. Now, I want to take this guy a little bit further. We found the equation of the tangent plane. Now I want to find the equation of the normal line. So if you remember, this is the equation of the tangent plane to this surface at this point. Now we're going to come up with the equation of the line that's perpendicular to this surface at this point. Okay, now conveniently the same information can be used, because for a plane we needed a normal vector, which is what the gradient was, and for the equation of a line we need a direction vector. But since it's a normal line, we're going to be able to get away with using that same 4, 23, 17 for the coefficients on the parameter. So conveniently our x, y, and t are just, or x, y, and z are just going to be a matter of filling things in. If you remember from last chapter, a couple chapters ago, that would have been a 5, negative 2, 3. And then we have plus 4t, plus 23t, and plus 17t. So these were the coordinates for the point, and then these were the components from the direction vector for the line. Again, since it's a direction vector of a normal line, we're using that normal vector to come up with that. So here's the equation of the normal line to the surface at the point. All right, so now we're ready to talk about coming up with the equation of the tangent line to the intersection of surfaces. So let's suppose we have two surfaces that intersect. Their intersection is going to be some curve, and we're going to come up with the equation of the tangent line to that curve where they intersect at a particular point. Now, the book's got a picture of this on page 841, and they've got an example worked as well. I'm going to choose a different one, but I would certainly encourage you to take a look at that so that you can better visualize what it is you're finding. So, if you remember, we're coming up with the equation of a tangent line, which means we need two things. We need a point and we need a direction vector. Now, if we have two surfaces, let's say f of xyz equals 0 is one of them, and g of xyz is another one. We know that the gradient of f is normal to f, and we know that the gradient of g is normal to g, which means that if we take the gradient of f and we cross it with the gradient of g, that's going to be normal to both, and that's important, both the gradient of f and the gradient of g. Now this is again where I think it'd be nice if you guys took a look in your book on page 841. In the picture they've got very clearly drawn out there the gradient of f, the gradient of g, and then the cross product being exactly what we want, pointing in the same direction as the tangent line for the intersection. So that's going to be the big takeaway from this, which is very, very difficult for me to draw on the screen, but page 841's got a nice picture of there with you with a cylinder and a plane. So let's go ahead and I'll clear the screen, we'll take a look at an example, and you'll see how direct this actually is. Okay, so we're going to come up with the parametric equations for the tangent line where these intersect. So if these intersect, it's going to be at a curve. We're going to find the tangent line to that curve at this point right here. Now, as pointed out in the last discussion, we're going to need these two functions. We're going to have f of x, y, z. And so for the first one, I'm going to say x squared plus y squared minus z. So to set this equal to 0, I just subtracted that over. And then our g of x, y, z would be a 2x squared plus 3y squared plus z squared minus 9. Now, the gradient of f will be the parcel of f with respect to x, with respect to y, and with respect to z of this guy. And then same thing here for the gradient of g. So for the gradient of f, we'll have a 2x, we'll have a 2y, we'll have a minus 1. And for the gradient of g, that's going to be a 4x, a 6y, and a 2z. I'll need to evaluate both of these at the point 1, negative 1, 2. And in doing so, we find out the gradient of f is going to be 2, negative 1, and the gradient of g is going to be 4, negative 6, 4. So now, if I take both of these and cross them, that's going to give me a new vector. Remember, when we cross two things, we get a new vector. That vector is going to be perpendicular to both the gradient of f and the gradient of g, pointing in the direction that we need for the line of intersection. Remember, direction vector is needed for the line of intersection. So, gradient of f, cross gradient of g. And now remember, the cross product is not commutative, but for the purposes that we need, it won't matter, because if we reverse the order, it's only going to change one of them to a negative, which isn't going to change the direction vector in a way that's going to affect the final outcome. So you've got a little bit of room here to interchange these if you so choose. So we have our I, J, and K. We have a 2, negative 1, a 4, negative 6, 4. And if I cross this, I'll get a 7, a 6, and a 2. So the equation of the tangent lines, we've got x, we've got y, we've got z. This being the point that we're using, we'll have those 1, negative 1, and 2, and then plus 7t, 6t, and 2t for that one. So plus 7t, and then plus 6t, and plus 2t. So this would be the parametric equation of the tangent line to the intersection of these surfaces. So once we get past the idea that given the gradient of f and the gradient of g are perpendicular to both gradient of f, gradient of g, we're able to cross these and come up with that direction vector that we're actually wanting to use in our answer.